Hello, welcome to my easy statistics. In this video, I am going to discuss about quadratic curve linear regression. Linear regression is a straight line relationship between independent variable and the dependent variable. If the relationship is not a straight line relationship, it must be nonlinear regression. So in nonlinear regression, quadratic curve linear regression is one of the model. So in this case study, we are going to discuss this quadratic curve linear regression, and we are going to investigate the relationship between height and weight. And this is a comparative study where we are going to have two models. One is a linear model, the other one is a quadratic model, and we are going to see which is the best model which is going to represent the data. The aim of this analysis is to find which analysis, the linear or quadratic model, is a best model for this data. Null hypothesis, we are going to have there is no significant relationship between height and weight. Now we have taken 55 individuals data and did the analysis on SPSS software. Now I am going to open the software, I am going to show you the data, do the analysis and discuss the results in an elaborated way. So this is a SPSS file where we have height in centimeters, weight in kilograms. Total 55 respondent data is there with us. Now we will start the analysis. Analyze regression in regression curve estimation. In this, a dependent variable is weight in kilograms and height in centimeters. Now we are going to select a model. Linear is by default, it is there. We will select quadratic and we will select this check button, display ANOVA table. Click OK. Now we are in the output screen. Here you can see the model description. In the model description, we are going to have two equations. One is for linear equation, the other one is for quadratic. And we already know the dependent variable is in weight in kgs. And the equation for linear is y is equal to a plus bx plus c. Okay, this is a straight line linear regression. But quadratic equation is y is equal to ax square plus bx plus c. This is the equation for quadratic equation. Y is equal to ax square plus bx plus c, where y is a dependent variable and x is an independent variable. A, B, C are determined by using a least square regression algorithm. Now the model summary, we already know there are 55 individual data is available, and both weight and height, both we have 55 respondents. Now this is a model summary for linear regression. Okay, R value is 0.598. This means that there is a moderate positive correlation between height and weight. R square value is 0.357. This means that 35.7% of the variance in the weight was explained by the height. Now adjusted R square value 0.345. This means that 34.5% of the variance in the weight can be explained by the height after taking into the account the number of variables in the model. Standardized error for the estimation. The standardized error for estimation is 0.8879. 8.879. This means that the predicted value of the weights are typically within 8.879 kilograms of the actual values. This is the ANOVA table. The ANOVA table shows the results of the analysis of variance test for the linear regression model. The ANOVA test is used to determine whether there is a statistical significant relationship between the independent variable and the dependent variable. The ANOVA table shows F statistic is 29.485 and P value is 0.000. This means that the relationship between the weight and height is statistically significant at a 0.05 level. In other words, there is a statistical significance difference between the average weight of the people of different heights. Now if you see, the mean square of regression is 2324.610 and the mean square of error is 78.841. The ratio of MSR to MSC is also known as F statistic is 29.485. This means that the variation in weight that is explained by height is much greater than the variation in weight that is unexplained by the height. The p-value is 0.000, which indicates the probability of obtaining the observed results by the chance is very low. This means that we can be confident that the relationship between height and weight is not due to chance. Now this is coefficient value regression analysis, where we have unstandardized coefficient value, standardized coefficient value, and we have significant value also. So B is the coefficient of unstandardized coefficient for the independent variable. The B coefficient for height is 0.891. This means that for every 1 unit increase in the height, we can expect the weight to increase by 0.891 kilograms. And the standardized value, that is the beta value, is 0.598. This means that height is a moderately strong predictor of the weight. Significant value is 0.05, means the height is able to predict significantly the weight. Now coming to model summary of quadratic. Now R value for quadratic model is 0.695. R square is 0.482, which is greater than the one which we have seen for linear. For linear, what we have seen is the R square value is 0.357. Okay, for quadratic it is 0.482, means the quadratic model, the independent variable is able to explain more variance on the dependent variable. So we can understand from this the quadratic model is better than linear model. This is an important point which you must write in the interpretation. For quadratic model, the R square value is 0.482, which is more than the R square value for the linear model. Right, and other things you can directly explain as we already discussed. This is the important point. You must identify the R square value for linear regression, R square value for the quadratic value also. After that, ANOVA table, already we discussed for the linear model. Same thing you must see, the significant value must be less than 0.05. Now the main important point is these coefficients for quadratic model. Here you are going to have two variables, two coefficients. One is height. The first one we can see, this is the height one. The second one is height square. Okay, so if you see the height unstandardized coefficient, it is in minus. It means if the height is increasing, weight is decreasing. In the second one, if you see height square, it is positive. It is 0.065. It means if the height is increasing, weight is also increasing. This is quadratic effect. At one time, the relationship is different. That is, if height increases, weight is decreasing. But after some time, what is happening? If height is increasing, weight is also increasing. I'll show you this with the help of the curve. You can see this curve. In linear, this dark line, the straight line, is a linear regression. It's continuously increasing. But this is not the best model. The best model already we discussed, quadratic model. In the quadratic model, you can see this model is in a parabolic shape. In the sense, from 130 centimeters to 150 centimeters. If the height is increasing, the weight is decreasing. But after 150 centimeters, if the height is increasing, weight is also increasing. This is quadratic model. Initially it is minus sign, means height increase, weight decrease. But after 150 centimeters, if the height is increasing, weight is also increasing. This we can see from the coefficient values. Height in centimeters minus 19.054. It mean that if the height increased by 1 unit, the weight is decreasing by 19.054 units, and this is significant because the significant value is less than 0.05. And height square, if the height increases by 1 unit, weight also increases by 0.065 units. This is also significant. And even the intercept, that is 1446.612, this is also significant. Now I have written all the interpretation here in this analysis. Now at the last we can conclude that the quadratic model is better than the linear model. I hope this analysis will help you in your research. Thank you.